Welcome to this explainer. Today, we're diving into a fundamental and frankly mind-bending conflict in the very architecture of our universe. We're going to look closely at how massive objects travel through space versus how light travels. And I promise you, by the end of this, the way you look at a simple beam of light, or even just a piece of blank paper sitting on your desk, is going to completely change. So let's kick things off with a cosmic mystery. In a perfectly uniform mathematical universe, the theoretical spherical cow model, gravity and harmony align beautifully. But in our real universe, things get pretty complicated. Mass gets dragged down, its path bending and warping depending on exactly where it is. Yet a photon of light, it just blasts right through, always finding the straightest, most perfect mathematical line. Why the difference? Since we're dealing with some pretty high-level theoretical physics today, here's our roadmap. We'll be covering 1. The gravity track paradox, 2. Mass and the zero limit, 3. Light and the one limit, 4. QED phase cancellation, and finally, 5. The silver mean bridge. Let's get right into it. Section 1. The gravity track paradox. Okay, let's dive into this first part and look at why mass actually needs a physical guide rail just to move. When mass travels through space, it's fundamentally at the mercy of the medium it passes through. You see, real planets and stars aren't perfectly uniform. They have incredibly dense cores, kind of like Earth's iron center. This creates what physicists call a Pareto distribution. Essentially, it's a power loss spike, where a massive amount of density is crammed into a tiny core, leaving a long, sparse, fat tail stretching outward. Because of this changing density, mass gets dragged right into that compounding fat tail. It constantly loses energy and momentum as its local geometric track bends, literally forcing the object's path to constantly change its scaling rule. If you look at how these probability fields shrink, it perfectly illustrates the problem. Errors in complex systems, or in this case, massive bodies, accumulate as a power function. Think of it like a mistake or a drag factor in one generation being inherited and then multiplied by the next. It causes this asymmetric drag. So massive particles are basically forced to trade off kinetic speed and geometry, meaning their path through space is, well, it's always a compromise. Section 2, Mass and the Zero Limit. Now, let's explore how we actually mathematically define this heavy, collapsing behavior of mass within the fabric of the universe. To do this, we have to look at the structural boundaries of space itself. We anchor this using a geometric parameter called d. You can think of d as the lens of resolution, or the decay rate of the space we're looking at. And when we push that parameter to the absolute bottom, meaning as d approaches zero, we hit what's known as the mass stack limit. In this incredibly dense zero limit, the field of view stretches into a hyper-narrow, infinitely tall stack. The area vanishes rapidly with every single step. This geometry perfectly mimics a dense mass core, or maybe a deeply compressed information stack in a computer that's just forcing computation to grind to a total halt. It's a high-decay power law zone, where space packs tightly into regional state buckets to secure mass and store data. All right, Section 3. Light and the one limit. Let's shift gears and look at the exact opposite extreme. How on earth does a photon of light completely ignore this dense, shifting gravitational trap? Well, unlike mass, light operates at the completely other end of the mathematical spectrum. When our geometric parameter d approaches 1, we hit the true flat line limit for photons. In this limit, the vertical height shrinks and the field of view forms a perfect, uniform 1x1 flat square box. Because d is 1, the decay rate is effectively 0. A photon travels at a constant speed, c, escaping that compounding power law lattice decay entirely. It just doesn't apply to it. This perfectly juxtaposes our two physical limits. On one side, as d approaches 0, mass packs tightly into area-contracting zones, those regional state buckets, struggling through shifting gravity profiles and power law crashes. But on the other side, as d approaches 1, light travels linearly, 0 lattice decay. It acts as a pristine, localized quantum entity whose energy state updates linearly without ever blurring or smearing its original geometric identity. It stays completely bit-perfect. Moving on to Section 4, QED phase cancellation. Now here is the absolutely crucial point. If light is traveling through the exact same lumpy, massive universe that we are, why does the photon get to stay on a straight line? Seriously, why doesn't it get pulled into those messy, curved tracks? To understand this, we have to look at Richard Feynman's quantum electrodynamics, or QED for short. You see, a photon doesn't operate by rolling down a physical macroeconomic groove or some geometric guide rail like a marble. No. Instead, light acts as a probability wave that samples the entire infinite context space simultaneously. It's mathematically trying out literally every possible path at once. And here is how the universe self-corrects. When a photon fires from point A to point B, its quantum phase clock is rotating. For any paths that stray away from the straightest, most optimal line, those phase clocks arrive at the destination wildly out of sync. Because they're pointing in opposite directions, they destructively interfere. They completely cancel each other out to zero. QED effectively prunes away all the chaotic spatial gunk, leaving absolutely nothing behind but the stationary phase trajectory, the straight, null geodesic. The bad paths literally annihilate each other mathematically. Which brings us to section 5, the silver mean bridge. So we've got mass, living in the extreme zero limit, full of lattice decay. And we have light living in the infinite one limit, traveling perfectly straight at constant speed c. We need a geometric peacemaker to bridge these two realities, right? Otherwise, the universe tears itself apart. Enter this specific number, the square root of 2 minus 1. This is known as the silver mean or the silver ratio. It's the exact rational coordinate that balances this whole cosmic architecture. Think of it as the ultimate diamond equilibrium, sitting directly between the zero limit of mass and the one limit of light. At this exact resonance, as we can see broken down here, the internal partition of a unit tile perfectly composes itself. It divides into its own sublenses without a single drop of spatial or computational approximation error. It ensures that as resolution shifts, the grid remains an incredibly stable, bit-perfect surface. And in an amazing twist, you probably interact with this profound cosmic stabilizer every single day. Seriously. This exact ratio governs the ISO 216 standard, which you probably just know as standard A4 paper. By fixing the aspect ratio to the square root of 2, every time you fold that paper in half to make an A5 or an A6 size, the subunits remain perfectly self-similar shards of the whole. That piece of paper on your desk, it's a tangible, forensic baseline of the exact, bit-perfect scaling law that bridges the gap between mass and light. So when you look at how light navigates space, mathematically erasing the wrong turns through QED phase cancellation to isolate that straight null geodesic, and how the silver mean perfectly balances the extremes of mass and energy without error, it really makes you wonder, is our universe just a massive self-correcting computational grid where the bad paths literally edit themselves out of existence? I'll leave you with that provocative thought. I really hope this explainer has changed the way you view the very fabric of light and mass around you. Until next time, keep questioning the reality you see.